So I'm not going into the advanced topics and so on. Three things I want to discuss in these lectures. First, to give an introduction to dynamics. I mean, I'm sure as students of physics, you're all familiar with these things, but still I think it will be advantageous to have a relook at the notion of dynamics, single particle system, n particle systems, and but specifically to look at these dynamics as initial value problems. I don't know how far this notion of initial values have been introduced to you in your basic courses, but I would like to make specific point that the dynamics has to be considered as initial value problem. What are these initial value and why they are important? So you are all studying differential equations and so on and so forth, but it's not only the differential equations, but the initial conditions are very important. And so we are going to ask the question, how these initial values can influence the development of dynamics. And nonlinear dynamics is basically concerned with the consequence of initial values. So I would like to make an introduction to dynamics from this point of view. And then I will discuss linear and nonlinear forces. Correspondingly, linear dynamics and nonlinear dynamics. Again, many of these things I'm sure you should be knowing, but I will make an introduction. But I will also discuss a number of specific examples, like starting from free particles and then constant force, linear harmonic oscillator and so on, damped, forced and so on. And then I will introduce different kinds of nonlinear oscillators and discuss the significance of initial values and sensitiveness to initial values, initial conditions, and ultimately leading to the notion of integrability and chaos. So in the last part of my second lecture, I will introduce the notion of bifurcations, chaos, complexity, also integrable aspects, solitons and so on. Just, I hope I can make a simple introduction to these notions. So as students of science, students of physics, so we are all concerned with making predictions. And the common theme in which science dwells upon, I would say, so what do you say will be the common theme of nature? What do you think could be considered as the common theme when you consider different entities in this universe? What could be the common theme? I believe it is the notion of change. Change is inevitable. Everything changes. Nothing is permanent. Animals are born, they grow and die. So do plants. Planets move around all the time. Chemicals interact. Clouds on the air, they all the time change. Everything changes. Even inanimate things like this table, planet, this walls, etc. If you wait for 10 years, 20 years, 50 years, 100 years, they do change. So nothing is permanent. Change alone is unchanging. So this is what Lord Krishna tells to Arjuna. Okay. Change is unchanging, is the thing that doesn't change. So the notion of the important aspect of science should be to explain this change and then to make predictions based on our understanding. So idea of considering this change, the evolution as a function of time constitutes the study of dynamics. So dynamics evolution as a function of time. So this notion has been understood by our great Indian philosophers, sages, saints, and so on. But in modern times, 300, 400 years ago, this was put in an appropriate scientific form in the form of the 3 laws of motion, which everybody knows. All of you as students of physics, from your school days onwards, you know that the great Isaac Newton had introduced this notion of change. In particular, he identified the cause. And then these 3 laws, the first law says that every particle continues in its state of rest or of uniform motion unless acted upon by force. So any system, any physical system, the beautiful notion you can introduce as a particle under appropriate circumstance, you can treat the system as a particle. This is a very beautiful notion because that allows you to associate any physical system with appropriate geometry. So the notion of particle, which is nothing but mass point associated with mass and attributed with other physical properties like charge, angular momentum, other things, and so on. So every particle continues in the state of rest or of uniform motion unless acted upon by force. But the second law, which is the most crucial one, where Newton talks of change. So you talk of position and momentum. The rate of change of momentum is directly proportional to the force acting on the system, external and internal forces acting on the system. So any particle and every particle in this universe is being acted upon by one or more forces. So changes will take place. You can't avoid that. So that is the law of nature. So, and Isaac Newton had put this in an appropriate form. The rate of change of momentum is directly proportional to the force acting on the system. And then the third law, for every action, there's an equal and opposite reaction and so on. But we consider Isaac Newton is perhaps to be the greatest intellect ever to be born, because he not only gave these 3 basic laws, but he also went on to prescribe how to utilize or how to make use of these laws for making prediction. So he identified the logical language with which we can pursue these consequences of these 3 laws, and he invented the art of calculating changes, namely calculus, the differential calculus. And as a consequence, you can put all these statements in the form of appropriate language, mathematical language, in terms of differential equations, differential calculus, and so on. So you consider, for example, a single particle system in a 3-dimensional Euclidean space, x, y, z. So you consider an entity, a physical entity, which you can treat as a mass point, a point which is associated, attributed with other physical properties like mass, charge, and other properties. Okay? So let me consider a mass point, a point which I can call as P, and I can, since it's a point, I can associate a vector at a given instant, say initial instant, as vector RT. So this vector R in the 3-dimensional Euclidean space has 3 components, x, y, z, which are all functions of t, the time. Okay? And then when this mass point is being acted upon by a force F, then it starts evolving in this 3-dimensional space. It follows a trajectory. So at a future instant of time, this is t initial instant, and at a future instant of time, it is at a point r of t. So the problem is then how to find r of t, and then the momentum, p equal to mass into velocity. So given the position r, you try to find and you associate the state with position r at t and p at t, which is nothing but m, the velocity, which is nothing but m d at the rate of change of position dr by dt. So the second law states that the rate of change of momentum is directly proportional to the force acting on the system. Dp by dt is directly proportional to. Without loss of generality, you can take the proportionality constant as 1. So you have dp by dt equal to f. And f could be a function of what? F could be a function of position, then momentum or the velocity. So dr by dt, and then any external influence, which is a function of time. Okay? And then p equal to m dr by dt, and m could be also a function of time in general, but in most situations m can be treated as constant. If it is not, then you have to also treat the time evolution. So if you treat mass as a constant, then you have m d square r by dt square equal to f r dr by dt t. Okay. So you end up with a differential equation. If you know the form of the force, if you prescribe the force, for example, when planets move around the sun, so what kind of force you have? Inverse square type gravitational force. Okay. So if you have Hooke's law, for example, you have restoring force proportional to minus k to vector r, and so on. So if you know the force, and how do you know the form of the force? From physical observations, from experimentation. So that's where you connect the mathematical equation with the physics of the problem. Okay. So from observations, from experimentations, you can know the form of the force. Once you give the force, then you have a differential equation to describe that particular phenomena. But that is a mathematical entity. For example, you can have a pendulum, an oscillating pendulum. Okay, so you can give the form of the restoring force, for example. Okay, F could be proportional to magnitude, could be proportional to sine of theta and some vector and so on. And so different phenomena, you can associate the force with it. But like that, you can have infinite number of pendulums in this universe. So if you want to know about the dynamics of a particular pendulum, so what do? So this is a mathematical equation. Then you have to associate an appropriate initial condition. So once you specify the initial condition, so what are those initial conditions? So what is the nature of this differential equation? What kind of differential equation is this? It's a second order vector differential equations. So you have to specify as a function of time. So you have to specify how many initial conditions? 2, because second order, so you have to define 2 vectors. So there could be, you could be start at an appropriate or convenient time as initial time. So I will take that as 0, the time is 0. So given this evolution equation, subject to the initial conditions, so you have the Cauchy initial value problem given r of t0, which I call as 0 or of 0, and then dr by a convenient initial condition dr by dt at t equal to 0. So given these initial conditions, so what do these initial conditions do? That's what is very important. Why do you need these 2 initial conditions? You said you have second order differential equations, and then you associate 2 initial conditions. Why? Because when you undo this differentiation, what do you get? You solve this equation, you get the solution, which is the position at any instant of time, future instant of time. And what does that contain? It will contain two arbitrary constants. So, but you are considering a specific motion of a particular pendulum, specific pendulum. There is no arbitrariness in that. So, in order to remove that arbitrariness, you have to fix appropriate initial conditions. And where do these initial conditions come from? That again comes from observation. You pull the pendulum apart, you allow it to oscillate. So, you start the stop clock, so you know the initial position and initial velocity, the maximum amplitude, and the initial velocity, for example, is 0. So, that fixes the nature of this differential equation. Then you associate the mathematical entity with the actual physical problem. So, there could be thousands of pendulum in this universe, but the one which you want to understand, by associating the appropriate initial conditions, you remove the non-uniqueness in the differential equations, the arbitrariness in the differential equations. So, subject to this initial condition, you ask the question, you follow this differential equation, then this mathematical entity will follow exactly, or will tell you exactly what happens to the physical system. So, this equation essentially takes life. As time evolves, your physical system follows this mathematical equation. It's as good as following the physical system itself, the mathematical equation. If you have correctly identified the force acting on the system, then this mathematical equation can represent the physical behavior in its entirety. So, you have given the initial condition, find R of t for all t greater than 0. So, that is the Cauchy initial value problem. Once you know R of t, you can also find dr by dt, and so the momentum, and so the state of the system, which you can follow for all future instant of time. Okay. From the initial value R of 0 and dr by dt at time, the initial time, subject to the nature of the force, then following the Newton's equation of motion and solving it, you can follow the physical system for all future times. So, that is the idea behind the Newton's equation of motion, how you associate a physical system with appropriate mathematical equation. You can extend this analysis appropriately to, and this is for one particle system. So, for an n particle system, what do you do? Again, the same second law holds good. When you have a collection of n particles, again, the rate of change of momentum is directly proportional to the forces acting on the system. So, what do you do then? Again, in the three-dimensional space, you consider the combined behavior of these n particles. So, each particle is represented by an appropriate position vector. So, that is for one particle system. For an n particle system, so again, at a given instant of time, you have n particles which are specified by n vectors. Okay, at a given instant of time, say t equal to t naught. So, you make an observation R1 t equal to 0, R2 t, R3 t, etc., or Rn t. So, find associated with that, you have the corresponding mass m1, m2, etc., mn. So, at every instant, you have a photograph of these n particles, and then you follow those trajectory. So, correspondingly, you have the equation of motion, the rate of change of momentum when the masses are constant, m square d square Ri by dt square equal to. So, what is that? For ith particle, so I running from 1, 2 to n. So, what is the corresponding equation of motion for the ith particle? You have the ith force, the force acting on the ith particle, which will be a function of, now, which will be a function of all the position vectors, because one particle will be acted upon by all the remaining particles, R2, R3, Rn, etc. And sometimes they may even have self interactions. So R1, etc., Rn. Similarly, all the velocities dr1 by dt, etc., drn by dt, and then any external influence. So you have a system of n coupled vector differential equations. Each vector has three components, xi, yi, zi, and so on. So the initial value problem now, the problem is the Cauchy initial value problem given the position vectors Ri at time t equal to t naught and all the dRi's, the velocities at t equal to 0, I running from 1 to Tn, all the particles. Find RIT for all t greater than 0. Okay. Then you know the complete evolution of all these physical systems. It could be the n gas molecules in this room, 10 power 23 gas molecules in this room, or the entire solar system, the sun and all its planets, 8 planets, and so on and so forth. Okay. So even n particle system, you can write down the equations of motion provided you know the force acting on the system. So again, it's the initial value problem. Given the initial values, position and velocity, or position and momentum. Okay. Subject to this initial condition, you follow this system of coupled differential equations and try to find the solutions. Okay. Then you can follow the future behavior of this entire dynamical system. And that's the way, for example, you can try to find the average properties in this room, average properties like the pressure, the temperature, the volume, etc., of these particles. Okay. Then solving this, you can find the entire behavior of these systems. Of course, in this description, there are complications. So this is what made the great mathematical physicists Pierre Simon de Laplace towards the end of 19th century to claim that everything about the universe is known, because Newtonian mechanics tells that if you know these forces acting on all the particles in this system, in this universe, then I can solve this. However complicated the problem is, I can solve the problem. I can follow these particles in principle, their evolution in future, and so I can predict the behavior of this universe entirely. Of course, you know that there are pitfalls in this Newtonian formulation. There are situations where this is not exactly true. Of course, when you want to describe the 10 power dynamics of 10 power 23 particles, it's extremely large system. So in practice, to solve such a complex problem, for example, all the particles colliding, coming out, exchanging energy, and so on and so forth, it's so complicated problem. And moreover, we are not interested in the individual dynamics of individual atoms or molecules in this room. But what we are interested is only in the average properties, average mechanics, or statistical mechanics. So in that case, you modify the Newtonian mechanics. Restrictions are in this Newtonian mechanics. So when particles number n going to infinity, it's more useful to develop an average mechanics, a statistical mechanics, as Boltzmann had done, as other people, Gibbs and others have done. So statistical mechanics will be a more appropriate description for such a situation. And of course, you know that even for small number of particles, even for a single particle, when you go to microscopic world, given the initial position and velocity, or initial position and momentum, so I believe that I can give these two entities with infinite accuracy. But of course, you know, when you go to microscopic world, there is an intrinsic restrictions on prescribing these two initial conditions exactly. So you require when you have the Heisenberg uncertainty principle coming into picture. So you have to modify the Newtonian mechanics, and you require the requirement of quantum mechanics in microscopic world. So a more appropriate description is quantum mechanics. You have to modify. And then I said, given the position, yes, the position is that you have the infinite universe. The particle can be anywhere, and you can measure that. There is no restriction. So the velocity at t equal to 0. There is no restriction in the Newtonian mechanics. And of course, you know that any material particles in this universe cannot travel with velocity greater than that of the light. Only light can travel with velocity of light, but any other material particle can approach the velocity of light, but it can never travel with the velocity of light. So there is an upper bound. So you have to bring in that restriction also. So when you consider the restriction on the velocity, then you have the relativistic mechanics. You have to modify the Newtonian approach with relativistic mechanics. But till now, I have not bothered about the form of the force, the nature of the force. So this is what in the past 4 or 5 decades, particularly starting from 1960s, it has been realized that the nature of the force can also dramatically alter your understanding of the way in which a physical system behaves, whether it's a single particle or many particle system and so on. So depending on whether the force is linear or non-linear. So does it make any difference? So what is this linear and non-linear force? What is this non-linear force? And what kind of changes one can look for? And that is where the importance of significance of initial conditions play a crucial role. Okay. So depending on the nature of the force, in particular when it is a non-linear force, you have the underlying mathematical description, the equations of motion, they become set of non-linear differential equations. When the forces are linear, you have essentially a system of linear differential equations. Linear differential equations, they are all characterized by well-defined property. So what is the basic property underlying linear differential equations? What is the most basic property underlying linear differential equations? That means the nature of the solutions. What is the basic? So it is the linear superposition principle. So it's not simply superposition principle, because you can have non-linear superposition principle. So linear differential equations are characterized by linear superposition principle. So what does that mean? So you have, for an nth order differential equations, you can have n linearly independent solutions. And now these n linearly independent solutions, you can superpose them. You can superpose them in a linear way. You can combine these solutions in a linear way. Still it will be a solution, a possible solution. So this kind of linearly combining the independent solutions. What is linear independent solution? We will come to that. So combining these independent solutions in a linear way, that is also leads to a possible solution. Okay. And that is the basis of all the methods that have been developed during the past 300 years or so on to solve differential equations, whether they're ordinary differential equations or partial differential equations or integral equations or integral differential equations and so on. So, for example, the Laplace transform, the Fourier transform, the spectral transforms, the Green's function techniques, all of them are based on this linear superposition principle. Okay, you know the linear vector spaces, the Hilbert space, and so on and so forth. So all of them are based on this notion of linear superposition principle. But once you have a nonlinear differential equation, this linear superposition principle fails completely. There is no exception for any linear differential equation. Starting from first order differential equations, the linear superposition principle fails. That means all the mathematical tricks, mathematical techniques, you know, and the mathematical properties, you know, of the solutions of differential equations, they in general they fail. So each differential equation, each nonlinear differential equation becomes a class by itself. So you have to investigate each differential equation on its own, and you may come across with new properties. And that's what happens. And the consequence of which these various notions of bifurcations, integrability, chaos, solitons, solitary waves, and so on, complexity, and so on and so forth, which are being invented every time as you investigate newer and newer differential equations. And over and above that, you ask the question, suppose I want to quantize this nonlinear system, the new solutions you have obtained, and so on. That leads to further complexity, notion of quantum chaos, quantum synchronization, and all kinds of newer concepts that emerge. So I will try to point out some of these basic notions. So any questions or comments or doubts that you have at this point of time? You want to make any? Of course, these are all quite familiar to all of you, I'm sure, or you have learned. But the important point I want to emphasize at this level is that it's not only the equations of motion, the differential equations, but it is the initial value problem which you associate with the evolution of a physical system. It's not only the differential equation is a mathematical entity, but only when you associate appropriate initial conditions, when you consider more general situations, when n goes to infinity in a continuous way and so on, you will have to also bring into picture the boundary conditions. But it is all the Cauchy initial value problem which one has to keep in mind. And then you ask the question, as the system evolves, how these changes in the initial states, in the initial conditions, can affect the evolution of the physical system. You change the initial condition, for example, slightly, can it make great change? And Henry Poincaré, during the beginning of the 20th century, when he started analyzing the three-body problem, of course, all of you have studied two-body problem, the Kepler problem. And the two-body problem, Kepler problem is nothing but the inverse square particle moving under the action of inverse square attractive force. Okay. And this problem, two-body problem, you can convert into an effective one-body problem. How? You can separate out the motion of the center of mass. The remaining effective mass problem is essentially an one-body problem. And that problem you can solve exactly analytically. And the consequence of which is, when you solve the one-body problem under inverse square type force, what do you get? What is the consequence? The consequences are the three Kepler's laws. Every planet moves around the sun in elliptical orbits, equal areas are swept out in equal time, and so on. Okay. So that problem is solved, even though it's a nonlinear problem. So I will define why it's nonlinear and so on. It's a typical nonlinear problem, but still it's solvable. It's an integrable problem, integrable nonlinear dynamical system. Then you consider the effect of a second planet, the sun, the earth, and a third planet, for example, Mars. So the effect of Mars would be a small perturbation to the main inverse square type force. So what is the consequence of this additional interaction? So this is the three-body problem which Poincare wanted to solve. And even as early as 1905, he came to the conclusion that this problem is not solvable. Essentially because a small change in the initial condition can lead to very large change in the final state of the system. Small errors that you introduce in the beginning can lead to very large error, in a finite time. And this is what in 1964 or 5, the MIT atmospheric physicist Edward Lorenz, in the study of weather dynamics. Weather dynamics is studied essentially by solving the underlying Navier-Stokes equations for the weather. And he converted this problem, reduced the problem to the bare minimum into a system of 3 first-order coupled differential equations. And he solved it by numerical, in those days, 1964, by numerical analysis. And he came to the conclusion, and which he put it in a dramatic way, a butterfly fluttering its wings somewhere in the Amazons. Where is Amazon? In South America, in the South American forests. A butterfly fluttering its wings somewhere in the Amazons can lead to a tornado, a cyclone-like situation in the state of Texas. And where is Texas? In the North American, United States. So in a few days' time, had the butterfly not fluttered its wings on that particular day, the weather would have developed in a particular way, in a very regular way. Just because the butterfly fluttered its wings, so there was very small change in the initial state of the weather, and that change led to a tornado in the state of Texas. Just to exemplify the kind of change that you can expect, small changes can lead to very large changes. So prediction of weather becomes extremely difficult. Short term, yes, you can make prediction, but long term, particularly, for example, around the equator and so on, predicting weather over a long period of time is almost impossible. Essentially because the Navier-Stokes equation is a very complicated system of nonlinear partial differential equations and so on. So you can solve through supercomputers by prescribing appropriate initial conditions, etc., all over the globe. There could be always errors in making observations and so on. So these errors can lead to very large deviations in due course and so on. It can become. So consequence of nonlinearity, because of this influence of initial conditions on the evolution of physical systems, so can be enormous. But at the same time, very orderly structures can emerge. In 2004, December 26, tsunami, though it's very destructive, but overall its structure is essentially very beautiful structure, very orderly structure. It's a localized wave, traveling over very large distances, thousands of kilometers, as far as away the Somali coast and so on. And most of the time it can travel without change of form or diminution of speed and so on. So very orderly structures can emerge. So nonlinear forces can sometimes lead to very orderly structures, can sometimes lead to very complex structure and so on. So even very simple oscillator with the introduction of nonlinear force can lead to very complex behavior. All kinds of changes can take place. As you play around with the value of the control parameter, the parameters which are in your control, which you can externally control. As you change, the dynamics can change from very orderly periodic structure to very complex structure through series of what one calls bifurcations, that critical parameter values, sudden qualitative changes can emerge, and ultimately into complex structures called chaotic structure, etc. So when a system can behave in an orderly way, when a system can behave in a complex way and so on, is a problem cannot be traced exactly at present, but these are all very challenging problems. So I will try to point out some of these. So I will start with evolution equations, the simplest form. Start from the most simple form, the Newtonian equation, when there is no force, F equal to 0, which is a very trivial case, and which is also a very idealized situation, because in nature, no physical system can be without one or more kinds of forces. But still, one can consider a situation where no force acts on the system, and that too in one dimension. So let me consider some of the simplest situations. So the second part of my talk is associated with linear and nonlinear forces. And correspondingly, I will consider linear and nonlinear dynamics in the simplest form. So I hope to introduce the notion of integrability, chaos, and all that, even with simple kind of example. So let me start with the free particle examples. One, a free particle. So most of the examples I will start with one dimension R, for example, just as is in one dimension. Okay. So what is the free particle equation in one dimension? Rate of change of momentum is directly proportional to the force acting on the system. And the force is 0. Free particle means F equal to 0. F again has got one component, Fx, F 0, 0. So what is the equation of motion? So equation of motion is M is constant. So m d square x by dt square, which I can write as x double dot. So dot means d by dt. Simple notation. Mx double dot equal to 0. Or in other words, x double dot equal to 0. Okay. So what kind of equation is this? D square x by dt square equal to 0. What kind of equation is this? It's a second order ordinary differential equation. So what kind we will see. So this you can trivially integrate. You can integrate once. So you get x dot equal to constant, which I call as I1, the first integral. I can integrate once more. So what do you get? X of t equal to I1 t plus I2, a second integral. Okay. Now this differential equation, second order differential equation, it has got two solutions, independent solutions. What are they? Constant, which I can take without loss of generality, is 1. What is the other solution? T. So two solutions. T1 and T. Okay. And then this solution is I1T, I2 into 1. So I1, I2 are arbitrary constants. So what have I done then with the two solutions? I have linearly summed up. So linearly superposed. So what kind of differential equation is this then? then I can call this as a linear differential equations. Okay. So how do I find these two solutions are linearly independent? I find, check the Wronskian. So what is this Wronskian? You write the solutions 1, t, and then, so take their first derivative. So first derivative is 0, and this one is 1. So what is the value of this Wronskian? Is 1. It's non-zero. So any non-zero Wronskian has a non-zero value, and then the corresponding functions are linearly independent. So you have two linearly independent solutions, 1 and t, and I have linearly summed up. Okay, so it's a linear differential equation. And so the corresponding dynamics, linear dynamics. But another important aspect is that I can also find two integrals. The integral I1 is x dot, and the integral I2 is, once I know I dot, the integral I2 is x minus I1t. Okay. Now, knowing these two integrals is equivalent to solving this problem. Okay? Because I can invert x dot equal to I1 and x equal to I1t plus I2. So I can find the state of the system uniquely. So this problem is an integrable problem. In the sense I can find the two independent integrals. Okay. So I can either solve this problem completely analytically, or I can find the associated integrals, two integrals, independent integrals. That is equivalent to solving this problem. So that you can keep in mind. So finding the actual solution is also equivalent to finding appropriate integrals of motion. So later on, you have different kinds of integrability. You can associate Hamiltonian integrability, Liouville integrability, and so on. But this is the simple notion of identifying integrals and integrability. Okay? How, knowing the integrals, you can solve the problem. Just use this. From this integrals, you can find the complete solution. And then the initial value problem, of course. Okay. I have the solution x dot. So if x dot initially the particle is at rest, what does it imply? X dot equal to 0. So I1 equal to 0. Then x equal to at t equal to 0, x sub 0 equal to I2. And then we saw that I1 is always 0. So x2 continues to be I2, which is a constant. So the particle is at rest, it doesn't move, and it continues to be at rest. This is what part of the first law. Every particle continues in state of rest when no force acts on the system, no force. The particle is at rest. Then second part of the first law, uniform velocity. If the particle moves with uniform velocity, constant velocity, the particle continues to move with uniform motion. Okay? So the second law, the Newton's first law follows. Unequivocal for a free particle. Okay. Now I take the next case. So it's trivial, but a lot of interesting aspects can come out as far as future dynamics is concerned. Integrability, the Newton's first law, and linearity of the nature of the equation of motion, and so on. So the next example is a constant force. F equal to A. So the equation of motion is mx double dot, again one dimension, equal to A. In other words, x dot equal to, or let me call it A prime, and x double dot equal to A prime by A prime by M, which I call as A. Okay. Which is again a trivial equation. You can easily integrate, and what is the solution that you get? You do one integration, you get x dot equal to, do one integration, x double dot equal to A, x dot equal to AT plus I1. Integration constant is very important. Then x of t, do one more integration, x of t equal to AT square by 2 plus I1t plus I2, the second integral. So again, I can know I1, the first integral is x dot minus AT, and second integral is x minus AT square by 2 minus I1t. So knowing I1 and I2, I can always find the solution. So these two are the integrals. Either you solve, obtain the full solution, or you find the two integrals that is equivalent to solving the problem. Okay. And what are these solutions? Again, this t and 1, they are the solutions of, so this differential, what kind of differential equation is this? Second order inhomogeneous equation. Inhomogeneity comes from this factor A. Okay. So now the solution is t is constant I2 into 1. Okay. T and 1. We have already seen that they are two linearly independent solutions of the homogeneous part. And what about this AT square by 2? What about AT square by 2? They are the particular solutions of this differential equation. Okay. So here you have a particular solution plus the linear superposition of the homogeneous part. So that is again a solution. So this is also a kind of linear superposition principle. Okay. So this is a linear differential equation. Okay. But inhomogeneous. Linear inhomogeneous second order differential equation. Ordinary differential equation. So this is particular integral. And this is, these two are linearly independent solutions of the homogeneous part. This one, these two. Yeah, combinedly you also call as complementary function. Okay. And then you apply the initial conditions, initial value problem. So x of 0, to start with, let us take the simplest situation. X of 0 is 0, x dot of 0 is the initial velocity, which I call as u. Then what do you get? This is x dot of at t equal to 0. X dot of 0 equal to I1. So which means I1 equal to u. So for all future time, x dot equal to, which is nothing but you call as final velocity v equal to u plus at. And x of t equal to, what is it? At t equal to 0, I2, x of 0 is 0. So I2 is 0. And so, and I1 is u. So you have I1 is u plus ut plus of at square. And this is the standard rule, you know, under constant force. Okay. As the solution of the initial value problem. Final velocity equal to initial velocity plus at, and final position, you have this parabolic function coming into picture. So that is these are all trivially known, but still to look from this point of view is quite interesting. Now I take a little more, just I will take 5 minutes and then conclude. The linear harmonic oscillator. Can I remove this? One-dimensional linear harmonic oscillator, which is also similar to a simple pendulum. Simple pendulum, which you do experiments in the school days. A pendulum you pull apart and allow it to oscillate. You start the stop clock and you calculate the period and calculate the total time from which you calculate the period. And then you check that t equal to 2 pi square root of L by G. So how do you come to that conclusion? You can do that problem or a simple problem. Simple harmonic oscillator or a linear harmonic oscillator. Okay. Again, one dimension. So what is the force? You pull the pendulum apart. It starts moving towards the equilibrium point. Okay. So what is the nature of the force? F equal to restoring force. So the force constant I call as K into x. So the equation of motion is what is the equation of motion? Mx double dot equal to minus kx. In other words, x double dot plus k by m, which I call as omega naught square for convenience. 0. Omega naught square is nothing but k by m. So what is omega naught? Omega naught you call as natural frequency. Why natural? Because k is the force constant, m is mass, so it's all given. It's a natural frequency. Okay. You can apply an external force with a particular frequency, that is impressed frequency. This we call as a natural frequency, omega naught. So how do you solve this problem? Of course, this is also a trivial problem. How do you solve this? There are various ways of solving this. First, you can directly integrate. Of course, you have tricks to solve this kind of equations. Individual equation you can write. But you can also solve this. How do you solve? You multiply by an integrating factor. Integrating factor. So what is that integrating factor? Multiply throughout by an integrating factor. Not e to the power. e to the power omega. Well, simple form is the x dot. Multiply throughout by x dot. You get x dot, x double dot, plus omega naught square x dot x equal to 0. Okay?
That exponential thing is for first order, not for second order.
Yeah.
Yeah.
Okay. So, you can integrate this easily. What is that? Integrating once. What do you get? X dot square by 2. D by dt of x dot square by 2 is nothing but x double dot. Then this one, half omega naught square x square. That is equal to constant I1, or you can also call as energy electron. You'll find as energy or Hamiltonian and so on. So this also allows you to find a first integral in this procedure. Then what do you do? Do one more integration. How will you do that? Take this to the other side. E minus half omega naught square x square, multiply throughout by 2, and then bring all x dependent part to the left hand side. Make a separation of variable. So you get dx by square root of 2e minus x square equal to dt. Is that clear? How did I get x dot square equal to 2e minus omega naught square x square, omega naught square x square. So take the square root, x dot equal to square root of 2e minus omega naught square. Bring down, make a separation of variables. So dx this much. So this you can integrate. It's a standard integration, cos inverse or sine inverse. So as a consequence, you get the solution as x of t equal to, what is it? Some a prime, some a prime cos or sine, what is it? Omega naught t plus some delta, or write as I2. Because once you integrate dt, you will get t plus a constant. This constant is related to that. Because you have to take omega naught square factor outside, and then etc. If you do all that, you will get this. So there is a second integration here, I2. So you find what is I2. I leave it to you. You can also find I2. So for this problem also, you can find an integral which you call as energy or Hamiltonian, and a second integral, time dependent integral. Okay, that you can find x of t, x dot of t, divide, you get tan, and from that you can find delta. Okay, so finding these two integrals is equivalent to finding the solution. Okay. Now the initial value problem, which is the most. So what are the initial conditions? You pull the pendulum apart, it's the same as pendulum. You pull the pendulum apart, you start the stop clock, so t equal to 0, and measure this amplitude, that is the initial value. So I call that as some known value. And what is the, at that point of time, what is the corresponding velocity? 0. Simple initial condition, obvious, physically acceptable initial conditions. So what is the corresponding solution of the initial value problem? X of t. Solution of the initial value problem. Substitute x of 0 equal to a. So x of 0, cos 0, cos I2. Similarly, x dot of t equal to 0. You find I2 will be 0, and as a consequence you get cos omega naught t. And you learn several things from this form of the solution. This frequency omega naught is independent of this initial value. The frequency is independent of this initial value. And this form of this time dependent part is independent of the initial value. So you can plot these functions in several ways. So solution is x of t equal to solution of the initial value problem. X of t is a cos omega naught t. A is given initial value, and x dot of t or mx dot, mx dot or p equal to m minus m. What is p? Omega naught a sin omega naught t. Okay. Now plot the time series. So what is time series? X versus time. So that is what we call as time series. So initially, so this is some A or call as A. At t equal to 0, x equal to A. And then it oscillates periodically with period 2 pi by omega naught. So that is the time series. You can also equivalently represent this in the so-called phase plane or phase space. What is this phase space? This is x versus p, or simply x versus x dot, because it is just mass into velocity. So in the x dot space, you have x and you have x dot. So you start from initial value, initial time at some time, maximum value x equal to a, and x dot is 0 at that point. Then you follow x and x dot, you will find you have a closed curve moving in the anti-clockwise direction. Now, for a particular value of a, now change a by a small amount. Then you find, so change a to a plus delta a. Then you will find again that trajectory qualitatively follows the previous trajectory. Sorry. No great change. So this is for second value. Again change. Again you will have a concentric closed curve. So a closed trajectory in the phase space corresponds to periodic motion, because these are all periodic functions. What is periodic function? A function, f of t you call as periodic if it takes the same form after you change t by a constant, a particular constant, period. So here the period is 2 pi by omega naught. So any closed curve in the phase space or phase plane corresponds to a periodic trajectory. And these periodic trajectories are not sensitive to initial conditions. Change in the initial condition A does not make any great qualitative change. You can make a prediction. Okay. So this is the characteristic behavior of this harmonic oscillator, and so also any linear differential equation. Okay. I think my time is already up, so maybe I will continue next time. Yeah. So I will give you as homework for next day's lecture. What is the dynamics? You can try to explore. I will quickly, because that's very important for my further analysis tomorrow. For damped linear harmonic oscillator, this is also called linear harmonic oscillator. So what is the force? F equal to minus kx. Damping. How do you represent damping? Damping means you have friction, etc. So what should be its form? It should be proportional to x dot, the velocity. So kx minus some alpha x dot. Put an alpha prime. When you divide by m, you can call as alpha. Okay? So you have the equation of motion mx double dot plus kx plus alpha prime x dot equal to 0. So try to analyze this. Then next problem, the damped forced harmonic oscillator. The force is F equal to minus kx minus alpha prime x dot minus or plus F prime sin omega t or cos omega t, whichever form. So omega is different from omega naught. Okay, that's impressed frequency. So you have the corresponding equation of motion mx double dot plus kx plus alpha prime x dot equal to f prime sin omega t, and when you divide by m, k by m, write as omega naught square, alpha prime m as alpha, f prime by m as f. So you have a neat differential equation. So these are all linear differential equations. You can check. You will have two linearly independent functions. Linear combinations will be also solutions. Similarly, here this is an inhomogeneous equation. You will have a particular integral and you will have the complementary function. Okay? Subject to initial condition. So what is the dynamics underlying this? Then I am going to ask the question, I will add a term, for example, lambda x cube or sine proportion to sine x. Simplest is lambda x cube. You can add the lambda x square also, but that's somewhat more complicated. You add lambda x cube from symmetry point of view and so on. What is the nature of the equation? Whether linear superposition is valid. If not, what kind of solution you can expect? First, without damping, without forcing, then with damping, then with forcing also. You will find all kinds of complexity. So this is what we will see tomorrow. And that will lead to the notion of bifurcations, chaos, complexity, and so on. And some indication of what's known as solitary solution, or soliton-like structure. So I will try to introduce these notions tomorrow. So any questions, comments? So I have considered only simplest problem. Okay. I have not gone into any. So all these things you are supposed to know, but I'm simply repeating what you are supposed to know. Yeah, please. Yeah. Pardon? Yeah. Yes. Yeah, I would say sufficiently small. You know, when you do your experiments, so the pendulum equation, the pendulum dynamics, maybe I will take a pendulum. So the corresponding equation is ml theta double dot plus mg sin theta equal to 0. Okay. L is the angular momentum or whatever it is. So you can plus damping plus forcing extra. So I'm neglecting that. Theta double dot equal to G by L sin theta. Okay. So when you pull the pendulum apart, if you come up to this point and allow it to oscillate, the dynamics will be extremely different. Okay. But in your classroom, the experiment you do is you pull the pendulum apart to some extent and then allow it to oscillate. But if it is as small as possible, then this T equal to 2 pi root of L by G, L is the length, G is the acceleration due to gravity, will be exact. But if you increase the amplitude further, then you will find where if you wait for more and more time, the T may slightly change. So theta is sufficiently small, then you will find this formula is exact. Okay. So how small? That you will have to, your experimental accuracy or numerical accuracy. So if it is few degrees or few arcs, it will be exact. But as you increase this further and further, there may be inaccuracies in the 4th decimal or 5th decimal and so on coming up. Okay. Yeah. So that you can try. So when do you approximate sine theta, s theta? You can look at the table. So you will see that for some small values of theta, sine theta will be nearly equal to theta. But there will be, even for smallest value of theta, in the 8th decimal or 10th decimal, there will be some deviation. So you can, if you can neglect, your experiment cannot check all that. So to that order, sine theta is equal to theta. So that kind of approximation. Any other question? Yeah, because the rate of change of momentum. So it's second derivative.
Is it a property of the deterministic system that we have to always take the second order in derivative? Like if the Newton's equation of motion was in the order of third order of derivative of displacement. So did it become
No, as long as you accept the rate of change of momentum directly proportional to the force acting on it, you will get second order derivative. Okay. The highest derivative in that equation will be second derivative. Okay.
But is there any reason that it is always second order derivative? I mean,
Because the rate of change. So that's what Newton had invented differential calculus, how to express these changes. Okay. Calculus is nothing but the art of calculating the changes, infinitesimal changes. Okay. So when you introduce the notion of differentials, infinitesimal differentials, naturally this definition comes. Now people also talk of fractional calculus, okay, fractional order derivative and so on. So that is, I think, it's more complicated, more complex. But I think for the time being, it is the clear derivative. What Newton had identified seems to be the correct way of looking at it. As we see, check in the case of pendulum or any other macroscopic entities, unless you come to microscopic world or introduce other complications, Newton's equation of motion seems to be okay. It's correct. Okay, so if there are no more questions, thank you very much.